This is it, the series finale. Over 4 episodes, we've built a complete vocabulary for Agentic AI. Single agent loops in part 1, multi-agent collaboration in part 2, workflow structures in part 3, and reflection, human in the loop, and agentic RAG in part 4, all linked in the description. Today, we answer the 3 questions that every engineering leader actually cares about. Which framework should I use? How do I make this production ready? And how do I pick the right architecture for my specific use case? Let's ship it. Let's map every architecture pattern we've covered to the real frameworks you can use today. I'm going to walk through 9 of them. LangGraph is the most flexible option in the ecosystem. It supports DAG workflows and state machine patterns natively in Python. If you want maximum control over your agent's flow and don't mind writing more code, LangGraph is your go-to. It's the Swiss Army knife. CrewAI makes orchestrator-worker setups easy with role-based agent definitions. You define agents as roles. A researcher, a coder, a writer. Give them tools, and CrewAI handles the orchestration. Great for rapid prototyping, though you'll want something more customizable for complex production systems. Microsoft's AutoGen excels at peer-to-peer multi-agent conversations. It's designed for agents that talk to each other, debate, refine, and collaborate. If your architecture involves agents as equals rather than a hierarchy, AutoGen has the best abstractions. OpenAI's Swarm is lightweight and handoff-based. It's minimal by design. Agents are just functions with instructions, and handoffs are first-class primitives, perfect for routing and triage patterns. Amazon Bedrock Agents integrates natively with the AWS ecosystem for single-agent tool use. It connects directly to Lambda functions, S3, DynamoDB, and other AWS services. If your infrastructure is AWS native and your use case fits a single agent, this is the path of least resistance. AWS step functions combined with Bedrock gives you production-grade DAG pipelines, built-in retries, error handling, parallel execution, CloudWatch integration. For enterprise workflows that need to run reliably at scale on AWS, this is the gold standard. Claude Code provides agentic coding with direct file system access. It's a code act agent in a terminal. It can read files, write code, run tests, and iterate. Excellent for code migration, refactoring, and automation tasks. Semantic Kernel from Microsoft is enterprise-friendly and works well in .NET shops. It uses a plugin-based architecture for single-agent systems. If your team is C# native, this is the most natural fit. And DSPI takes a completely different approach, programmatic prompt optimization for pipeline architectures. Instead of manually writing prompts, you define the pipeline structure and DSPI optimizes the prompts automatically through training examples. It's research grade and powerful for teams willing to invest in the learning curve. For AWS native enterprise stacks, which is where most of our clients operate, the winning combination is Bedrock agents for straightforward single-agent workflows and step functions plus Bedrock for complex multi-step pipelines. For teams that need maximum flexibility and are comfortable managing Python infrastructure, LangGraph is the most capable choice. Building the agent is the easy part. Making it production-ready is where 80% of the effort goes. There are 5 critical concerns that will make or break your deployment. First, observability. Every single agent action needs to be logged. What was the input, what tool was called, what was returned, what decision was made, and why. Without this, debugging agent failures is like debugging a black box. You know the output is wrong, but you have no idea where the reasoning went sideways. The tooling options are Langsmith for LangChain and LangGraph stacks, Arise for general model observability, and custom CloudWatch dashboards for AWS native systems. Whichever you choose, make sure you can trace a single request through every agent and every tool call end-to-end. Second, cost control. Multi-agent systems can burn through tokens at an alarming rate. A single complex task might trigger dozens of LLM calls across multiple agents. Without guardrails, your monthly bill can spiral. 4 strategies. 1. Model tiering. Use your most expensive model only for the orchestrator and critical decisions. Workers use cheaper, faster models. 2. Token budgets. Set a maximum token spend per task and kill the workflow if it exceeds the budget. 3. Result caching. If a tool call produces the same result for the same input, cache it. Database schemas don't change between agent iterations. 4. Early exit. If the agent reaches high confidence before exhausting all steps, stop early rather than doing redundant verification. Third, error handling. Agents will fail. LLM calls timeout. Tools return unexpected results. APIs go down. Your architecture must be designed for failure from day one. The essentials? Retry with exponential backoff for transient failures. Fallback paths. If the primary tool fails, try an alternative. Dead letter queues for tasks that fail permanently so they can be reviewed and reprocessed later. And human escalation triggers when automated recovery isn't possible. Route to a human operator. Fourth, guardrails. Every boundary between agents and the outside world needs input and output validation. This means validating what goes into each agent and validating what comes out. For AWS native stacks, Amazon Bedrock Guardrails provides content policy enforcement out of the box. It can block harmful content, enforce topic restrictions, and validate output formats. For custom stacks, you need dedicated validation layers, schema validation for structured outputs, content filters for safety, and business logic checks for domain-specific rules. A common mistake is only putting guardrails at the edges, validating user input and final output. But agent-to-agent communication needs validation too. A hallucinated output from one agent becomes corrupted input for the next. And fifth, latency. Multi-agent systems are inherently slower than single-agent or deterministic systems. Every agent call adds network round-trip time plus LLM inference time. A 5-agent workflow with 2 iterations of reflection can easily take 30 to 60 seconds. 3 mitigation strategies. Parallelize. Use DAG structures to run independent agents simultaneously. Stream. For user-facing agents, stream tokens in real time so the user sees progress instead of waiting for a complete response. And go async. For background processing, use event-driven architectures where agents publish results and downstream agents subscribe to events. Now for the most practical part of the entire series, the architecture decision guide. Given a specific use case, which architecture should you choose? Let's walk through the most common enterprise scenarios. For code migration tasks, converting Hive to PySpark, migrating Databricks notebooks to EMR, transforming Oracle procedures to PostgreSQL, use plan and execute as your base, combined with a reflection loop for iterative improvement and a generator critic for validation. The planning ensures global coherence across the migration. The reflection loop catches bugs iteratively, and the critic validates semantic equivalence with the original code. For migration assessments, analyzing database schemas, building cost comparison models, mapping dependencies, use orchestrator-worker combined with a DAG pipeline. Specialized workers handle each analysis domain in parallel, while the orchestrator synthesizes the final assessment report. For interactive assistants, chatbots, copilots, and conversational tools, a single React agent with human-in-the-loop checkpoints keeps things responsive and safe. Don't over-engineer it. A well-prompted single agent with the right tools is remarkably effective for interactive use cases. For automated workflows like Jira, ticket generation, report creation, or ETL pipeline management, use a deterministic DAG pipeline with LLM nodes at key decision points. Most steps are predefined. The LLM only activates where judgment is needed. For cost optimization analysis, comparing cloud providers, modeling pricing scenarios, forecasting spend, a single agent with structured output is sufficient. The task is analytical, not generative. Give the agent pricing data, calculation tools, and a clear output schema. And for complex research tasks, multi-cloud comparisons, technology evaluations, competitive analysis, a multi-agent debate or research swarm delivers the most comprehensive results. Multiple agents independently research different angles, then debate or synthesize their findings. And here's the most important insight from this entire series. Most production systems end up as hybrids. an orchestrator-worker setup where each worker internally uses a react loop with reflection, a DAG pipeline where one node triggers a multi-agent debate for a critical decision. Don't feel locked into a single pattern. The best architectures compose multiple patterns to match the problem's actual complexity. Let's recap the entire series. In part 1, we built the foundation with single agent patterns, React for transparent reasoning, CodeAct for powerful code execution, and the tool use loop for efficient simplicity. In part 2, we scaled up with multi-agent architectures, orchestrator-worker for task decomposition, hierarchical for multi-domain complexity, peer-to-peer for quality assurance, and swarm for lightweight routing. In part 3, we added structure with workflow-based patterns, DAG pipelines for parallel execution, state machines for auditable control, and plan and execute for adaptive planning. In part 4, we made agents smarter with reflection for self-improvement, generator critic for quality assurance, human in the loop for production safety, and agentic RAG for intelligent retrieval. And today, in part 5, we mapped it all to real frameworks, covered the 5 production concerns, and built a decision guide for selecting the right architecture. Here's the takeaway that matters most. Architecture is not an afterthought. The pattern you choose determines your agent's reliability, cost, speed, and maintainability. Pick deliberately, start simple, and evolve your architecture as your requirements grow. Don't build a multi-agent swarm when a single React agent will do, but don't be afraid to level up when the problem demands it. If you found this series valuable, subscribe for more deep dives into AI architecture, cloud migration, and enterprise data engineering. And drop a comment. Which architecture pattern are you going to implement first? I want to know.